Let me just say, let me just make this in half hour, 40 minutes, because you look tired. So by 5:40 we are done, 45 we are done. Let me tell you what's going to be. It's a bit disconnected from the rest, not completely disconnected, but a bit disconnected. Let me motivate it in this way. In these examples that I was discussing yesterday, the one of the rat brains, the one of Cleveland, you see, if you look at them, okay, they are good doers to field theories that are basically young mills in the case of the Day4 rat brains, super young mills in the case of Cleveland, and then all the ultraviolet completion kicks in, right? So there are scalars, there are fermions. Typically, these things are supersymmetric. I mean, in those cases, in some cases are supersymmetric, in some cases are not. There are masses for the scalars. In the supersymmetric cases, they will be the same as the masses for the fermions, but not necessarily. And then some potential, right, for the scalars and the fermions. That in principle is possible to write. So notice that all these fields, especially in these examples of rat brains, since there are all examples coming from brains and rat brains, etc., all these fields are either in the adjoint of the gauge group, or in the case of Cleveland, in the bifundamental of the gauge group. In this case, because there are two gauge groups, okay? But in none of these cases, we have a field like a true flavor, like in QCD, right? Or like a true fundamental field, fundamental dynamical field. So these were not present in the examples we discussed. And you may say, well, okay, look, these theories, they do confine, they do have a non-trivial beta function, they do have anomalies, not anomalies of gauge symmetries, but anomalies of global symmetries. So they, in the case of Cleveland, you can even see a Goldstone. So there is a lot of interesting phenomenology, right? But there is something that is missing here. Let me motivate it in this way. If we were working with QCD, one would have, aside from this, the quarks and the anti-quarks. Let me represent them in this way. And if one has various quarks, that would induce an SU-NF cross SU-NF symmetry, right? That these systems were not presenting, right? They were not having any chiral symmetry. This is the word that one uses here. Okay? Okay, so you may say, well, so what, right? Having chiral symmetry actually changes a lot the spectrum, right? Because it's a global symmetry, and all the particles in the spectrum will come labeled by numbers under these symmetries, etc., etc. Actually, there is another observable that changes a lot the moment one has quarks, massless or massive. That is the following. Suppose that you compute, you introduce, as we did you introduce external, very heavy, unlike this one. These are light. Let me draw them like this. Quarks and anti-quarks, so non-dynamical quarks and anti-quarks. And if you have quarks present in your dynamics, right? So if you have quarks, dynamical quarks, what your Wilson loop will do is something like this. They will confine a bit, and then they are produced and will change. All these examples we are discussing, they are okay in this bit. and then they keep on confining. Okay? So there is a lot of different phenomenology, right? The moment you add this new symmetry into the game. Alright? Good. So the rest of the discussion is how can one add this symmetry in string dual. Okay? So what do I have to do in string dual to add new particles that will come with new symmetries? Okay? that's the goal of the discussion of what comes now. So let me, in order to have this discussion in a nice way, let me I hope that is clear that having new symmetries and having new particles will change a lot, right? Will change this, will change the beta functions, will change anomalies, will or will not add Goldstones if the symmetry is broken, etc., right? So it has lots of impact on the dynamics, especially the strongly coupled dynamics. So let me discuss this in a way that is, by the way, all this I'm taking from a review I wrote with Alfonso Ramalho and Angel Paredes, first sections that are really nice. I'm taking the discussion from there. Then I should say many of the things I was discussing are taken from here and there and different places. If any of you wants to read particularly about something, just ask me, and I for each one of the lectures there is 1 or 2 reviews that have been written by different people. Good. So let me go back to the 1970s and discuss 2 things that people discuss in those days, purely in a field theoretical setting, and then we will see how that field theoretical setting gets translated into modern or stringy language. Okay, you see, in all our thing, we are discussing the limit of NC going very large. Okay? Not necessarily strictly infinite, but large. And all the idea of, and this was an idea by Tuft, and his idea was actually that, again, completely in a field theoretical setting, his idea was that in taking this limit, many observables may get simplified and be expressed in this way, in a series like this, okay? And the expansion parameter he's introducing is basically 1 over NC, okay? In order to do so, he's forced to define a coupling that is not G and Mills, but this one, right? And he sees that this is the coupling that truly is controlling this expansion and many other things, any perturbative expansion. Okay? Very good. Now you may say, okay, I will add to this flavors. And you may wonder, okay, how many will I add? Well, I could add flavors in such a way that an F over LC is really very small, or I could add flavors in such a way that an F over LC is an F and NC are comparable, right? But I will always be working with NC very large, because I want to keep this picture of having a parametric expansion, right? And that picture is the one that, by the way, if you recollect, we were always needing to have large NC in order for the Toft coupling that we are defining that was going large. So this was going to small, this is going large, but this is large enough for our gravity approximation that typically was even something like this. The radius, so if you want, the Ricci scalar has to be controllable enough, or the radius of curvature have to be large enough for the gravity to be valid. Okay? So we were making the point since the very beginning that we want to work on spaces very free of any singularity, and that means that they should not pinch or anything that will imply a singularity of the same size of a string, right? So I would not like to have to correct my gravity solutions, okay? Good. So all in all, what I'm saying is that in all this string theory story, one is working in the large and limit, right? So this is taken, right? And then you can say, okay, I could work in the large and limit with a finite number of flavors, or I could work in the large and limit with a large number of flavors. Okay? So you may wonder, okay, what will be the differences if I do one thing or the other? And it's very instructive to look at how different diagrams. Let me draw. Okay. Let me draw a bit smaller because I would like to make 3 of them. How different diagrams scale. So these are going to be vacuum to vacuum diagrams. This is just a field theoretical estimate that I'm going to make. This is going to be a fundamental field, the one in the external line. It's going to be a fundamental field. And then I could have adjoint fields that I will indicate with these curvy lines just to indicate that this is like a gauge field. Okay? Or I could have adjoint fields and pair producing a fundamental. Or I could have adjoint fields, but in what's called a non-planar diagram, a diagram that cannot be drawn on a surface like this, but there is a jump there of one of the lines over here. Okay? So these are called non-planar diagrams. These are diagrams where there is a fundamental being pair produced, and this is a diagram where there are all adjoints inside, correct? And same here. So here I can consider a diagram with all adjoints, or a diagram where there is a pair production of fundamentals, or a diagram that is non-planar. Okay? And they will, all these diagrams, they will mediate some process that in this case is kind of a meson scattering. You see, you can think as a meson being inserted here and there, and fundamentals are being propagated there, but then these are all the quantum corrections to that. Okay? So remember that mesons are made out of fundamental fields, so you create a meson here, destroy it there, the fundamentals propagate, they destroy themselves, and these are all quantum corrections to that. Okay? So of course, we are not going to compute these diagrams, but I'm just going to tell you how they scale with NF and NC. Computing them involves computing terribly complicated integrals. We are not even going to bother with that. We're just going to look at their scaling with NF and NC. So this, by the way, I'm stealing from a physics report. In 1990, people wrote a physics report about different models. I can't tell you the reference, but the report is not very clear, but the appendix that it has is super clear, and this is spelled very nicely. So once again, we are always working in the limit in which this is fixed. In the gravity approximation is fixed and large, NC is going large, and NF can be fixed or large. Okay. A diagram like this, believe me this, in this scaling, scales like 1. In this scaling, scales like 1. So any diagram like this will contribute up to integrals factors of 1, okay, in an F and NC. A diagram like this, up to integrals, will scale like an F over NC to the 1 because there is one of these pair productions. A diagram like this will scale like an F over NC to the 1. Non-planar diagrams, you may have read this, are the ones that contribute to these kind of things. They are suppressed in this way, and similarly here, they are suppressed in this way. So notice that depending on the scaling you are working, and by the way, this scaling is associated with the name of Tuft, because was Tuft the one who proposed to scale things in this way. So take an F finite and an C very large, and it was Veneziano the one who proposed scaling this way. This is Veneziano in 1977, and this is Tuft in 1974. propose these two different scales. The point I want to make with this is the following. You see, if your number of flavors is 1, 2, 3, and your number of colors is large, 10, say 7, a diagram like this will contribute to the process. A diagram like this will be quite suppressed, right? And the more windows you add, the more will be suppressed. It's going to be 2 in that case, or more and more, right? So this is suppressed by, I don't know, we say 1/7, okay? This is suppressed by 1/49, right? So it's very good to just compute this one. That will give you a good approximation to the result, and then you correct or not, but you have a control approximation. If you go in this scaling, what this is telling you is that now you can no longer suppress the things that you were suppressing before. Okay? So these things will contribute. This will count as much as this, because this is a 1, basically, right? Or again, so you are taking an F7 and C7, that's a 1, or 6 or 7, right? That's a 1, basically. It's clear what I'm trying to say, right? Good. So you see that there are two different scalings that they will imply two different physics behaviors. In other words, to a same process, there will be two different kinds of diagrams contributing, and that will be qualitatively different physics. Okay, tell me.
This is a little bit
go.
something that may be a detour, so if it is, I'm happy to discuss it afterwards. So I guess that if I could attempt to ask my question is, these kind of arguments, do I understand them correctly in the sense that do they depend on the kind of diagram that you are computing? What I mean is, sorry, I mean this is very precise right now. You are discussing about vacuum diagrams, and in a given theory, I understand that this goes like 1/nc squared, for instance, in non-planar contribution. And I think that in that diagram you can also argue that there are not enough symmetry factors that can alter that scaling.
Indeed.
But you could, sorry, this is part of the question. I guess that what I've never understood is if I would be interested in computing other observables, which Tov would have also claimed that satisfy that expansion, the scaling with NC would still be the same, but you may actually have many diagrams, and so you may worry that the expansion breaks down.
You may have something like this.
Is this a fair comment? Because I've never really understood.
Let me give you an example of this. Let me give you an example of this.
I mean, this reminds me of VMN in some sense.
Very good, very good.
But this is why I don't want to have a detour.
There are no fundamentals in VMN, but this reminds you VMN because it may happen indeed, that you have so many of these.
Right.
That the thing that you thought was a 0 is no longer.
It's no longer.
Yes. Let me give you an example for this. Suppose that you take QCD with NC equals 10 to say something large, and 1 quark. Okay, 1 quark.
Yeah.
And on the other hand, you take QCD with NC equals 10 and 8 quarks. So let's make it of the same order. Right? 8, 9, 10, whatever, right?
Yeah.
You know what I mean. And then you may wonder, what happens if I compute the Wilson loop? It's a pity that Luigi is not here, because he will answer this question. Jamie can answer. What happens if you compute the Wilson loop? In this case, well, you will see far in the ultraviolet for small separations, a Coulomb-like law. Then you will see a confining law, and then you will not see this thing where the meson, where the pair was created. So I have the very heavy quarks, pair producing, and the very heavy anti-quark, so like this. So the mesons being created and living freely. You will not see that because this process is, in this case, 1/10 suppressed. Okay? Right? So I didn't make it brutal enough, but I put here a 20 and now it's really very suppressed. Right? So you will not see this process. So what you would think in this theory is that this theory actually confines, right? So it's really very suppressed, this process. In this case, you will see that. And the lattice see these things. This is what the lattice people call Quench approximation and quench approximation. Am I right? Good. Good. So here you see an example where what you are doing here, you may think it, the harmony would like this plot. This is the Wilson loop, and this is the line of fundamental. So what you are doing is cutting this line when you produce the meson, cutting this line. But when you do this, you are contracting an NC and an NF, so it's going to be NF over NC suppressed. Okay? So you see how, indeed, it's a matter of counting, because I have many of something, right? Many in this case of quarks, that the dynamics will be strictly changed. Okay? Is this clear as an example? Yes? So what I'm having in mind when considering the two scaling or the Venetiano scaling is precisely what the lattice person called the quench approximation, or in this case the unquench approximation. And it's very nice, and we can discuss later the way they do it, right? It's very tricky the way they do it. It's really very intelligent. We can discuss how they do it. Okay, let me discuss now how they do it. And I'm going to say that a very naive version of the quench approximation that I was told that I'm very naive, but I mean, it's correct what I'm going to say, but very naive. They do it in a much more intelligent way. Let me see if I remember this. Suppose that someone asks you to compute the vacuum polarization. Or let me say it this way. Suppose that someone asks you, okay, take QCD, the action of the gauge field plus the action of the fermions. And let me give them the mass, right? Because I will quench them due to the mass. Okay? So you may say, okay, I will do the integral over the fermions. Okay, do the integral over the fermions. You will have an effective action that you can write in this way. This is the action for the gauge field, and here you write the determinant. Okay, so this is something very complicated in the gauge field, but this is that. I've done nothing here actually, just the integral over the fermions. Now, doing that, first approximation is doing this. Okay, you can see that. And remember these formulas. How was this thing? Log det, sorry, it was log det of something is the trace of the log of something. Yeah, remember these things from, one learns these things in the quantum field theory course, etc. So instead of computing the log of the depth of the thing, you compute the trace of the log of the thing. Okay. This thing, you are going to take the m out. You're going to take it out, etc. Right? And you're going to expand this. Okay? So this gives you is log of 1 plus x. So the expansion I don't remember, but surely starts with right? 0 plus, etc., etc. So it's going to give you something like this. Sorry. This is times m. So it is log of m. Let me write it nicely. This is log of m plus log of this slash over m plus 1. Okay? Right? Right? So this gives you log of m, whatever it is. This gives you 1 plus this slash over m plus this slash over m squared, and go on. And there is a trace. Right? This one is a zero. This is a Fulrich theorem, that theorem that tells you that in 4 dimensions, this diagram is zero. This one is a zero. This one is this. Okay? So, one way of quenching the quarks is taking them very massive. Okay? So, because if you take them very massive, this is negligible. All your dynamics of this is just replaced by a constant, and your theory is basically Young-Mills. Okay? So what you have done, and it's very clear why you are quenching, because what you have done is you are avoiding pair production because this costs you 1 over m squared. Okay? So you are quenching by brute force. The lattice people do this in a much nicer way, introducing kind of ghost fields. They don't need the mass to be 0. And they cancel the determinant with something that they put. It's super nice. Okay? Am I right? That's the way Agostino explained it. So
Probably then.
okay. Now well, we can
don't
tell.
quench anymore, right?
Sorry.
There's no point in quenching anything anymore.
Oh, because you can now compute.
Yeah.
Okay, but you agree that during years was the thing, the only thing they could do, right?
Yeah.
Okay. So in that sense, people don't need to do this anymore because now their computers can, and they can study this well before they were limited to this. Okay. So so there is no point in quenching anymore. I thought.
Yeah, pretty much.
Okay.
You're right.
Very good. Okay. So coming back to Joan's question, you see how quenching is losing some dynamics, right? In this case, in this way, you are losing it because you are imposing that you will lose it, because you are imposing that it will cost you a lot, this, right? But it will not cost you in this sense, but it will cost you because you will not pair produce, okay? Quenching in this sense, it costs you in the factor thing, and in the other sense, okay, so I think we are more or less on the same page. Is this okay? Physics-wise, yeah?
But I think that just to, because I feel a little bit sensitive with this because I'm not a field theorist.
Me either.
And whenever I ask this question to field theorists, eventually I think that people realizes that what worries me about these arguments is coming from black hole physics. And so using ADS CFT, something is going on. I think what I'm trying to say is that these expansions are generically, for any observable, they are generically of the form that you are saying.
Yeah.
But imagine that instead of computing vacuum diagrams, I want to compute correlation functions in very heavy states in my field theory. So imagine that I am in a conformal field theory and I use the correspondence between operators and states. This means that I'm computing one of your observables, but I'm not doing it in the vacuum. So that's equivalent of doing a vacuum correlation function of an extraordinarily heavy object. So just by big contraction, let's say, there could be a huge degeneracy factor that can compete with this expansion. So actually, I don't necessarily buy these
counting arguments
when the entropy of your states actually can be very large. And actually, this is not just a technical point. I mean, I want to believe that this is important for black hole physics and things like that if you want to do calculations in ADS.
Are you thinking, Joan, so instead of vacuum to vacuum, something where I'm adding and coming out with very heavy states, something like that you're thinking?
I mean, I'm thinking of computing 2-point functions, just to make it simple, but instead of doing it in the vacuum, doing it in a non-trivial state, which happens to have a mass of the order of n squared in whatever n's that you have.
So your point is that you will produce so many things running that they will overtake the
I mean, I know that from particle physics perspective, this is a question that you would hardly ever ask.
Right.
Because this is a highly...
Yeah, because they don't do that.
Exactly.
Yeah.
But from the perspective of a gravity person, which is my interest,
right.
I think that this could break down this
Yeah. I'm sure.
So
I'm sure. If you
exactly,
for some reason you have to
make
put a number
right.
here,
Yeah.
right? That overtakes. That's very clear. Yes. And your point is, when saying a very heavy state, is that very heavy state will allow so many things to go
there are
here.
too many processes to take care of that.
Very good. So I hope it's clear the difference between a theory being quenched and a theory being unquenched, and generically this is what happens, and more or less, okay? So it's very nice to see that the string theory knows both things, and knows it in a very nice way. So let me Let me talk about that, and that will be the bottom line of the thing. How the string theory does this, how the string theory does that. Okay? And the time is already over. Okay. So the first thing is how to add these labels. Okay, so that's the first thing. How to add them into the dynamics. Remember that. Okay, let's first think brain picture wise this thing. Suppose that you have some D3 brains. NC of them. Okay. Good. So on these D3 brains, let's forget about gravity and everything. Just think about the brains in flat space, right? So this is all very weak coupling, etc., etc. So okay, in here I will have a Young-Mills coupling that will be basically G string. Okay. And suppose that I have here a set of, let me take it this way, and have these 7 brains, and now we'll see why these 7s and etc. etc. Okay, we will go over this. Such that these 7 brains are sharing these 3 plus 1 dimensions, and then extended on some 4 manifold big enough. Okay. On these 3 brains, this is the action, and I'm going to suppress all the other terms. On these 7 brains, this is the action. And this action is in 8 dimensions, and this action is in 4 dimensions. Okay, so these are the 7s, these are. So notice that if you were to put everything as an effective 4D theory, you could do something. This is just a way of motivating the thing. This should perhaps be thought in a different way, but let's just motivate it this way. Suppose that you reduce this so that you bring this to a 4D theory. So what could you do? You would separate these directions from the 4 directions, and then here I will have cage fields, whatever other particles I have, fermions, whatever. Okay. So notice the following. This thing here is playing the role, so this is the 7-dimensional Young-Mills. This is playing the role of 1 over an effective 4-dimensional coupling.
So you mean 8-dimensional Young-Mills or 7?
8. So this was for the 7 brain, it's an 8. Okay, it's an 8. Right. So this thing here is playing the role of a 4D effective coupling, right? So notice the following. Notice the following. If this space is large enough, in principle, if I make it infinite, this will be infinite. That means that the 4D effective coupling is 0. Okay? Right? So you may want to think that the dynamics of these things gets frozen, right? Gets decoupled. Okay? Now let's remind something that we discussed in some of the second lecture. The dynamics of these things is described by open strings that begin and end on the D3 brains. They are the ones that will produce your n equals 4 super Young-Mills. The dynamics of these things is described by brains that end and open on 7 brains, and they will produce this 8-dimensional super Young-Mills theory. There is also the strings that begin and one and end in the other. Okay? They will produce, and this, please believe me here, they will produce 4-dimensional fields that transform in this gauge group and in this gauge group. Okay? The trick point here is that since this gauge group, because of this limit, is decoupling, now these fields will transform under SUN C gauge group and also under SUNF global group because the gauge coupling is 0. Okay? Right? So it's a quick, dirty argument, but the idea is to make you believe that the way to add these fundamentals is to add objects that typically are higher dimensional branes into the system, okay? And add them in such a way that they are non-compactified in a non-compact manifold, okay? So that to kill their gauge coupling and make this a global gauge, a global group, okay? Is this more or less believable, please?
Is there any reason for not using D5?
No. The only reason why I'm not using F5 is that in ADS5 x S5, this is the way that we use supersymmetric flavors. But if you do it with D5, you know, it's the DP plus 4, right? The thing that is SUSY. It will give you non-SUSY flavors. Okay. Bad thing? No. Okay. But this is just an example. But indeed, with D5s, it works exactly the same. Just put it on a non-compact 2 manifold. It will be a non-SUSY manifold, so that's why the thing will not preserve SUSY. But the argument will go exactly the same. People will complain to you, oh, it's not stable, this will come into this. Yeah. Okay, all right? It's the same kind of thing. All right? So what's interesting about this is the following. The string theory knows these two things in the following way. If you have a background, right? And now let's think everything with ADS5 x S5. Suppose that you have a background that's ADS5 x S5. Okay? So is the background generated by this NC, these 3 branes. On that background, you're going to put these 7 branes. Okay? Okay, how are you going to put them? Okay, there are 2 possibilities. One is making a probe, and the other is back reacting with them. Okay? So you can, the probe, you will be able to do it if NF over NC is small enough. And the back reaction, you will have to do it every time that NF and NC are comparable. Okay? Right? Because there will be effects that you will not be able to ignore. But in principle, what you're doing is you are supplementing the action of type 2B. That was the action that was giving place to the ADS5 x S5 via these 3 branes. You are supplementing it with the action of the branes. That is the Dirac-Born-Winkel plus Besumino. And this will have the follow that scale there. So you see, in the case in which NF over NC is really small, you just freeze the gravity background, you just freeze your ADS5 x S5, and you just study your Dirac-Born-Winkel action plus your Besumino action, and now let's be more specific. It's going to be an action in 8 dimensions because these are going to be 7 branes. There's going to be e to the minus dilaton, that's part of the Dirac-Born-Winkel action. The determinant of the induced metric. If there are P fields or any other gauge fields, you'll have to put them there. And here you will have the Besumino term, right? For those of you who are not familiar with the Dirac-Born-Winkel action, never mind, it's the action of a membrane. There is a tension and there is a charge, right? So one term is the tension of the membrane, the other is the charge of the membrane. The point I want to make is the following. These fields are pullbacks of the fields on ADS5 x S5 when pulled back over the brane. In this case here, that I will refresh in a second. In this case here, in which you back react, you will have to put on equal footing, like we are doing here, the type to be action and the born-infant Besumino action. Right? All together, so you have to add this thing here and compute the equations of motion, and you will have to solve again, right? So this is a more complicated system because aside from the type to be equations of motion, you will have supplemented by this thing, right? You will have to do the variation respect to the metric, variation respect to the Ramond fields, etc., etc. Your system will change. Okay. So notice the following: if you start with ADS 5 crosses 5, and you just probe it, right? You are not changing the geometry ADS 5 crosses 5. And what you are studying is the dynamics of the brain on that background, right? The background tells the brain how to move. The brain does not talk to the background. This, by the way, is exactly the same you were doing when you were young, and your teacher told you, I have a charge, I have a probe charge, compute the electric field of this, and you are giving this thing, right? So this was a probe. This was not changing the field configuration here, okay? What you're doing in the second example is when your teacher was telling you, I have a charge and I have another charge. Compute the field here, and you have to sum the field of this and the field of that. Okay? Right? So you are, okay, this problem is linear, this is not linear, but here you are not back reacting, you are only probing. In there you are back reacting, so you are non-probing. Good.
What fixes this relative NFL latency coefficient? Is there some anomaly in flow or something?
No. Let me say it in this very good. Let me say it in this way. The fact that there is an NF here, you believe it because I have to put as many as Planar brains I have. Okay? I can put them all together, in which case it's going to be the non-abelian born-infant action, messy. But I can put them all slightly separated, and it's going to be the abelian, and that will pick up an NF. You agree? So where I'm getting the NC from? Well, this one will scale with an NC, right? So I could put it in this way. Let me now go to the point that you want to make. But this is another way of saying that it's nice to be said in this way. This thing that I'm going to say is not easy to see if you're not working out an example, but just believe me at this level. Suppose that you are working with ADS 5 crosses 5, right? So just this particular example, right? Just to make things more or less understandable. There is an F5 here, and that's the only flux that is turned on. This will be the equation of motion in that case, right? There is no H3, there is no nothing else. If you turn on this thing, right? And for example, you turn on gauge fields on this brain, there will be a term here that will be like this. Okay? So this equation actually will be modified in this way. When I do the derivative with respect to C4, I will get something like this. Right? So if I do the probe limit, I'm missing to solve the Bianchi identity, which will translate, in some cases, in the fact that the field theory could be anomalous. But I will not see it, because I will not see this. Okay? If I back react, I will have to solve it that way, and this will enter into the equations of motion. I will be solving that one. Okay? Okay? So the tricky point about not back reacting is that there is information that you are missing, just like you are missing information in not using that diagram and yes using this diagram. Okay? Right? So it's two approximations that people have done. There are many papers where people have been doing the probe. There are many papers where people have been back reacting. And it's very nice to see how in observables, especially in things related to black holes, having those flavors change slightly the calculations. And I can tell Joan if he wants later which are the papers that do that calculation specifically. It's not me, but okay.
It's okay. Can I ask another question?
Yeah.
And maybe you are going to say this now, but since I've never followed this, I think I understand the different approximations in the what you have called quench and unquench. I think that what I'm having a little bit more of difficulty, and I think I'm just missing, if you could say a little bit about the philosophy, I would appreciate it. So I understand that the degrees of freedom in the quench approximation are given by the effective action that you wrote. You have a type 2b, which is fixed, and then you have the degrees of freedom on the D7 ring,
Exactly.
which is this effective action in some fixed background. I think that what I'm lacking, hopefully because of lack of experience, but I feel that I am missing something more, is coming back to the way in which you have motivated from a purely field theory, because now you are trying to give us a bulk dual description of your tough arguments. So if you want to compute an observable in the gauge theory, you have arguments telling us that the corrections go like NF divided by NC, and you have just derived that by answering Paul's question. But I guess that how do you actually use this effective action to actually compute the strongly coupled version of this correction? I mean, this depends on the observable, I guess, but if you would take your Wilson loop or something, how would you do it? Because this is describing the D7, right?
Very.
So the way in which you taught us how to compute the Wilson loop was using the Walsh action of the string. So how do you put these things together in the quench approximation? Or is this just as a bleeding effect? Or?
Very. So 2 comments there. One, how your question can be answered with 2 different answers. One is, for example, so you're asking, how is the Wilson loop noticing? The presence of the D7s?
Yeah, for instance.
And another question that is maybe not the one that you were asking, but can also be asked, or maybe it's just continuation of yours, is how correlators
Good. Yeah, very good.
will notice the presence of the D7.
Yeah, exactly. Yeah.
Excellent. Good. So let me first tell you about the Wilson loops thing. Okay. So what you have here is some ADS bulk. Let me. Okay. By the way, is it clear to you and to all of you that if I do this thing and I solve the new equations of motion, the background will change, and whatever I compute will have the NF there written, right? So here it's very clear.
This is clear, yeah.
Right? So here is the thing. How will the Wilson loop notice that something is happening? Okay, so this is your bulk, right? And you are putting these D7s, I don't know, in some. So they are sharing the 4 dimensions, and they are in some non-compact format. Okay, this is your Minkowski dilation. Okay. Now, how I compute the Wilson loop? Well, I put the D3 brane very far away, as we discussed the other day. I let string hang, and this string will describe a profile, etc. I will have, if I do this with care, I will have more than one solution. There will be one solution that will be the one that we discussed, right?
Yeah.
That gives you that potential that we know. But there will be another solution with less energy, up to a given separation. There will be another solution with less energy, where this will get attached to the D7 brane. Right? So there are 2 solutions here. So think it. This is the picture that Andreas Karch will draw for you. This is the D3. This is your end of space, and these are your D7s that they could be here, or they could be distributed somewhere there, right? So, okay. So there will be some strings that are hanging up to there. Then you can stretch even more. They're hanging up to there. Then you can stretch even more. They will be hanging up to there. But then there is some stretching where for the string it's better to attach to the D7 than to take the curve, right? And it can happen, right? Because string can end on the D brane,
Yeah.
right? So
But
this.
is this a calculation that is argued without doing a calculation?
No.
or
They
you
do.
a-
By the way.
Because you have argued to us that the background doesn't change. Therefore,
Very good. So you have to be tricky in the
Sorry
following
for being
sense. No.
technical, but-
Very good. Very good. If you do blindly the calculation that we discussed, right, on Tuesday, I don't know what day was it,
Yeah.
Tuesday, Wednesday, what you will get is what we got,
exactly. Right.
right? Square root of lambda over n.
And I understand that it can end on DD7.
Right.
It
Right.
makes sense, but
Good. If you, but here is the tricky point.
Uh-huh.
Here you have to realize that aside from the solution you are considering, there is another solution that will have less energy up to a given separation. Right? So, for example, for separations like this, solutions that end on the D7 have more energy, so they are not realized. Right? Solution up to separation like this, same. But there is some separation where for the string is more convenient,
okay.
right, to end on the D7, right? And that's what will change this law into something that, okay, that would be your, if you want, that would be your screening, right, in this sense. But you have to be tricky. On the other hand, if you take this, if you take these solutions, there you will see
You will see it
explicitly,
explicitly,
right? And you will see it because these solutions know about these processes, and this pair creation is the pair creation. These solutions do not know about that process, so you have to force on it.
Yeah.
Okay? Okay?
Yeah.
How compute correlators? How to compute correlators? Because that, okay, this one, okay, you force it there, etc., etc. I will say this and we cut it, Joan, because people are hating us.
Yeah, I'm sorry. You can just decide not to answer.
No.
We
Let's
can
say this
discuss
because
afterwards.
it's nice, and if not, we discuss it later. So, there are many papers that have done this, but one that I like particularly is one by David Mateos and a fellow called Patiño, if I'm not wrong. Okay, so it's David and this fellow. What they do is the following, that is something is completely correct and natural. So they are saying, okay, we have a D7 here, right? So let's remember the Gabsa-Clairaut-Polyakov story in the gravity approximation. What you are doing was the action of type 2D supergravity with the boundary values, etc., etc. This you are equating to the partition function of your field theory with currents, given the boundary values of the fields in the currents. Okay? So what they are doing is they are improving this by adding here the Born-Infeld action. Born-Infeld Besuminov.
Yeah.
And they are thinking, okay, look, if I add here, if in this Born-Infeld action I have, aside from induced metric, some gauge field, this gauge field will be the thing that when going to the boundary will give place to a vectorial current. Okay, so here you will be improving it in this way.
Good.
Okay, so then they do two derivatives of this respect to a vectorial current, and they are computing the current correlator. That is like computing two derivatives of this respect to the boundary value of A, right? And you see here, and this is very nice because you see here how here is the color theory imposing dynamics on the flavor part, right? And not the flavor part imposing dynamics on the color. Okay? Right? So this is a pullback, so it's just like that. Right? So it's the color imposing the dynamics of the flavors. That's precisely this. Here the colors determine the dynamics of the flavors, right? Or if you want in more physics language, the glue balls impose the dynamics of the mesons, right? But not vice versa.
Not vice versa.
So this is what people have done. This is a very neat example. I like it very much. But you, in some cases you have to be tricky, like in this paper of Karch, where they observe that suddenly there is another solution with less energy. Right? There is also a very nice paper by Karch and Jaffe and someone else, whose name I will not remember now, where they do this at finite temperature and they see how there is screening at finite temperature. Super nice, super nice. And very delicate paper, very, very careful paper. All right, so since people hate me already and no one will come to the dinner, It's going to be me and Joan and the rest. Thanks very much for your attention. I will not bother again through Edinburgh in the next 3 years, I promise.
Okay, well, thank you
Thanks
very much, Carlos, for a fantastic set of lectures. So you gave lots of problems.